In this video, I'm going to discuss a little bit of the relative strengths of some acids lab. And so this lab is looking at equilibrium in the realm of acids and bases, and in particular with acids. And so it's going to be using what's called the Bronsted-Lowry acid and base. So that's a particular way of thinking about acids and bases, and this is the one that says that we have an acid here, and then when that combines with water, then that will go to equilibrium, and we will end up with our A here. So that's our conjugate base plus H3O plus. So this is kind of the basics of Bronsted-Lowry acids and bases. And so this is the way that we will be thinking about acids and bases in this lab. We won't be, well, I mean, we'll kind of get to what's called a Lewis acid, but I won't bog us down in too much of what that is. And so the relative strengths of acids has to do with the equilibrium, as I said. So in acids and bases, the equilibrium constant is K sub A. And so if we have something like hydrofluoric acid and hydrocyanic acid here, we see that the equation here is very similar. We have our acid here, we have our water, then we have our conjugate base, and then we have the H3O plus. And so if we didn't know the equilibrium, you'd think that these would just be equally strong acids. But we see here, and so I found these Ka's on Google. These are not actually listed in the lab notebook, I don't think. But anyway, we see that this one is 10 to the negative 4, and this is 10 to the negative 10. So this hydrofluoric acid is actually a lot stronger than this one. And so the reason for that is because if we look at our equilibrium equation, so if we look at our equilibrium equation, K sub A, and we have the products on top, which for this will be our F minus and our H3O plus on top. And so those are our products, not on the bottom. So we can sort of disregard the H2O because that is a liquid. But we have our H, well, in this case, I can put the F, but you can also see that this would be the same thing if we had the HCN, which would be on the bottom, and then up here on the top would be the CN. And so we see that if this Ka is much smaller, then we're going to have a lot more of the reactants down here than we will have of the products. And so this H3O plus will actually be a lot lower concentration for the HCN than it will be for the HF up here. And so that's sort of how these Ka's can be thought of as representing the strength of the acid. And so another thing that we will be having to think about in this lab is how to convert from concentration to pH. And so this right here is the equation for pH, which is just equal to the negative log base 10 of the H3O plus concentration. And so then if you want to go to concentration, because you have a pH, you take the 10 to the negative pH power, and that equals the concentration of the H3O plus. And so down here I have a couple examples. So if we have, say, a concentration of H3O plus that's 4.9 times 10 to the negative 5 molarity, we take the negative log of that, and that gives us a pH of 4.3, which is somewhat acidic, because remember, a pH equal to 7 is neutral, and so anything that's below 7 is acidic, and anything above 7 is basic or alkaline. Then say we are given a pH, so pH equals 3.3. We do 10 to the negative 3.3, and that gives us 5.01 times 10 to the negative 4 molarity. And so that is how you can go between the H3O plus concentration and the molarity. Then so the last thing I'm going to mention in this video, so we will be looking at these metals that have these waters complex to them. And so we see that when water is complex to it, because water doesn't have a charge, this is still a 3 plus charge. But one of these waters can actually lose an H plus to the solvent here. And so we end up with this H2O 6 here going down to H2O5. Then we end up with this OH here, and we see that the charge goes down to 2 plus because this OH has a negative charge and therefore neutralizes one of the positive charges from the aluminum, and we end up with H3O plus. And so that's how this metal can actually act like an acid. So if you go on to organic chemistry, and actually maybe later this semester in general chemistry, you learn about Lewis acids, which is what the aluminum is. But for in the Bronsted-Lowry model of acids, we can think of it this way as being able to lose this hydrogen to the solution to generate H3O plus, which is our acid in this case. But anyway, I hope you find this video helpful, and I will see you later.